Mayday, Mayday! Air Transat 236. The right engine has flamed out. We're down to just a few hundred kilograms of fuel left.
These were the chilling words of the captain of an Airbus A330 carrying 293 passengers and 13 crew members, flying halfway across the Atlantic Ocean. Just moments later, the crisis escalated dramatically as the left engine also failed, plunging the aircraft into complete darkness. The loss of both engines caused all electrical systems to switch to emergency mode. The cabin lights went out and oxygen masks deployed due to the sudden loss of cabin pressurization. In these dire circumstances, the pilots fought to maintain control of the powerless aircraft, their training and experience pushed to the limit. Meanwhile, the cabin crew scrambled to prepare passengers for a possible emergency water landing, fully aware of the slim odds of survival. This is the story of Air Transat Flight 236. On August 24, 2001, Air Transat Flight 236 departed Toronto Pearson International Airport in Canada, bound for Lisbon Airport in Portugal. The route, spanning the Atlantic Ocean, typically takes around 7 hours. The aircraft, an Airbus A330 equipped with 362 passenger seats, was built in 1999 and had logged over 10,000 flight hours by the time of the incident. For this transatlantic journey, it was fueled with approximately 46 tons of fuel. On Air Transat Flight 236, there were 9 tons of fuel on board at departure, 5.5 tons more than the legal minimum. In the cockpit were 2 pilots, 48-year-old Captain Robert Pichet, with nearly 17,700 flying hours, 800 of which were on the Airbus A330, and 28-year-old First Officer Dirk de Jager, with 4,800 flying hours, 386 of which were on this aircraft type. 4 days before the flight, the aircraft underwent routine maintenance. During this inspection, the maintenance team discovered metal flakes in the oil filter of an engine, indicating possible problems. Since the source of the flakes could not be determined, they decided to replace the engine. However, the new engine, borrowed from Rolls-Royce, was configured differently from the replaced engine, leading to complications. The rear hydraulic pump of the old engine proved incompatible with the fuel pump inlet tube of the new engine. Since service calls were not accessible at that time, the maintenance team followed the recommendations of the engineering department. They used only the fuel line from the old engine. This ensured sufficient space between the fuel line and the nearby hydraulic line. After installation, the work was inspected and a ground test of the engine went off without a hitch. The aircraft was approved for flight. At 1 a.m., the Airbus took off, heading east and climbing to a cruising altitude of 39,000 feet. The first few hours went smoothly, without a single problem. It seemed like a quiet, routine flight until halfway across the Atlantic. A few hours after departure, the pilots noticed something unusual. The secondary display for engine parameters showed abnormal data from the right engine: unusually high oil pressure, lower oil temperature, and a decrease in oil quantity. This behavior was inexplicable, since oil temperatures normally rise during flight. The pilots consulted the manual but could not find an explanation. They reported the problem to the maintenance center, which also could not find a cause. What no one knew at the time was that there was a serious fuel leak in the right engine. During the engine modification, the hydraulic and fuel lines had been placed too close together. Although the engineers thought there was enough space, they had not anticipated how the pressure in the hydraulic systems would affect these lines in flight. Continued friction eventually caused a crack in the fuel line, leading to a significant leak. According to the final report, the aircraft lost 12 to 15 tons of fuel per hour through this leak, a dramatic contrast to the normal fuel consumption of 2.6 tons per engine per hour. Despite the leak, the engine continued to operate normally, thanks to the design of the fuel system. The Airbus A330 has multiple fuel tanks, 2 in each wing, a central tank, and a trim tank in the horizontal stabilizer. The trim tank redistributes fuel from aft to forward to maintain the center of gravity. Normally, this tank is not emptied until 35 minutes before arrival, when the wing tanks drop below 4 tons. In this case, however, the trim tank started transferring all its remaining fuel to the wing tanks early. As a result, the available fuel was consumed faster, which only worsened an already critical situation. In the cockpit, the pilots did not immediately recognize the seriousness of the situation. While they were still dealing with the oil pressure problem, a warning message appeared on the ECAM electronic centralized aircraft monitoring system, the central display that alerts pilots when action is needed. The message reported a fuel imbalance between the tanks in the left and right wings. This means there is more fuel in one wing's tanks than in the other, upsetting the aircraft's balance. In the event of a fuel imbalance on the Airbus A330, the ECAM system does not give specific instructions. Instead, pilots are referred to the Quick Reference Handbook for guidance. Relying on their experience and simulator training, the captain chose not to consult the handbook. He opened the crossfeed valve and turned off the right-wing fuel pumps to transfer fuel from one side to the other. What the pilots did not know was that this action actually exacerbated the fuel leak. Fuel was now being transferred directly from the left-wing tank to the damaged system on the right side. Had they consulted the QRH, they would have been immediately warned not to proceed with the checklist if a fuel leak was suspected. Within 10 minutes, the pilots saw fuel levels dropping rapidly. They realized there was not enough fuel to reach Lisbon safely. In this critical situation, they began searching for alternative landing sites. Options were limited as they were over the vast Atlantic Ocean. They identified Lajes Airport on the island of Terceira in the Azores, Portugal, as a possible alternate base. As the pilots discussed their strategy for the detour, a cabin crew member reported into the cockpit with a report about passengers needing assistance. The pilots asked the crew to visually inspect the wings. The cabin crew dimmed the lights in the cabin and used a flashlight to look at the wings through the windows. Despite this inspection, no abnormalities were observed. A fuel leak would have been easily visible during the day, but in the darkness of the night, it was almost impossible to detect. Since there were no visual clues and the ECAM gave no additional warnings, the pilots concluded that the problem was probably a computer malfunction. Although the pilots consider running the standard procedure for fuel leaks, they decide not to.
Could it be a fuel leak? Should we start with the standard fuel leak procedure?
No. We would then have to descend to a lower altitude, which would worsen the situation.
Understood.
Investigators later concluded that if the pilots had followed any of the prescribed fuel leak procedures, whether it was an engine fuel leak, a wing fuel leak, or a non-localized fuel leak, they would have landed with at least 3.8 tons of fuel on board. The decision not to follow procedure was influenced by a cognitive thinking error known as framing bias. This occurs when people stick to one interpretation of a problem and pay attention only to information that supports that interpretation, while ignoring contradictory cues. In this case, the pilots believed the problem was a computer malfunction and focused on cues that confirmed that idea while overlooking other cues. Meanwhile, the pilots were swamped with tasks, communicating with maintenance control, running checklists, coordinating with cabin crew and air traffic control, and planning for emergency landing. In this hectic environment, they struggled to find a clear moment to carefully consider their options. The pilots took a moment to reconsider their earlier assumptions, as the fuel imbalance problem did not disappear despite previous attempts to transfer fuel between tanks. Fuel continued to leak rapidly. In response to the continued rapid decrease in fuel quantity, the crew switched on the right-wing fuel pumps and off the left-wing fuel pumps. This caused fuel to flow from the right-wing tanks to both engines. The pilots set course for Lajes Airport and alerted Santa Maria Air Traffic Control of their emergency landing, referring to a critical fuel shortage. At that time, the plane had only 7 tons of fuel left on board, which is only 6% of its total fuel capacity. Despite further attempts to adjust the fuel system with help from the maintenance center, the amount of fuel continued to decline at an alarming rate. Any remaining doubt disappeared when the right engine failed. This happened while the plane was at an altitude of 39,000 feet and was still 150 kilometers from the airport. The captain immediately increased the power of the remaining engine, but with one engine working, it was impossible to stay at this altitude. With only 600 kilograms of fuel left, a fraction of what was needed, the pilots realized the situation was life-threatening. The first officer declared an emergency over the radio.
Mayday, Mayday, Mayday! Air Transat 236. The right engine has flamed out, and we're down to just a few hundred kilograms of fuel left.
He then informed the cabin crew and passengers of a possible emergency landing at sea. 13 minutes after the right engine failed, and still 120 kilometers from Lajes, the left engine also failed. Without engine power, the aircraft lost its main electrical systems, leaving the cockpit shrouded in darkness. At the same time, cabin air pressure dropped, forcing the use of oxygen masks. The Airbus now lost its primary power source, but a crucial fail-safe mechanism, the ram air turbine, RAT, deployed automatically. This small turbine, powered by airflow, provided just enough electricity to keep key instruments and systems operational. Yet the aircraft lost essential features such as wing spoilers, nose wheel steering, and reversible thrust, which made maneuvering and landing considerably more difficult. The crew performed full engine failure procedures and began a glide to the airport. Air traffic control at Lajes flashed the runway lights on and off to help pilots locate the runway in the dark night. To stay airborne as long as possible, the captain maintained a descent speed between the recommended glide speed and the stall warning speed. It was crucial to stay high enough because once too low, there would be no way to regain altitude. However, the captain faced additional challenges. He had to keep the speed above 140 knots to keep the ram air turbine working, but stay below 200 knots to avoid difficulty deploying the landing gear. As they approached the airport, it appeared that his strategy of staying at altitude had worked too well. Instead of the usual approach at 3,000 feet 16 kilometers from the runway, the plane found itself at 13,000 feet, just 13 kilometers from the runway. The aircraft's altitude was far higher than expected, especially with no engine power to descend quickly. To address this, the captain executed a 360-degree turn, a maneuver commonly used in gliding to shed approximately 4,000 to 5,000 feet of altitude. Simultaneously, the first officer deployed the landing gear and adjusted the slats on the wing's leading edges. These measures were essential, as they provided additional lift and allowed the plane to decelerate without generating excessive drag. After completing the turn, the captain leveled the wings as they approached the runway. However, the aircraft was still at an altitude too high for a standard landing approach and too low to attempt another complete turn to lose more altitude. With no margin for error, every decision was critical as the plane neared the runway, leaving no room for retries. On final approach, the first officer closely monitored the airspeed, a critical factor since the lack of engine power meant the flaps couldn't be deployed. This necessitated a landing at a much higher speed of approximately 200 knots, compared to the usual 145 knots. The first officer played a pivotal role, consistently updating the captain on airspeed and altitude to help manage the challenging landing. Moments later, the aircraft hit the runway with significant force, causing 8 of the 12 tires to burst. The plane bounced back into the air briefly before touching down again, nearly 3,000 feet from the runway's threshold. As the plane sped along the runway, slowing it down became a major challenge. Key systems such as wing spoilers and engine reverse thrust typically critical for deceleration, were inoperable. To complicate matters further, the anti-skid system, designed to prevent the wheels from locking, failed to function properly. This caused the wheels to lock up as the captain applied the brakes. Despite these challenges, the aircraft managed to come to a stop just 600 feet short of the runway's end. Fires broke out in the left main landing gear due to the intense braking, escalating the emergency. Captain Pichet quickly ordered an evacuation. Remarkably, all passengers and crew members exited the aircraft within 90 seconds, ensuring their safety. Fire crews, already on standby, swiftly extinguished the flames. Incredibly, every passenger and crew member survived. This miraculous landing went down in history as the longest glide by a passenger aircraft with no fatalities. Initially, the crew was celebrated as heroes. However, as investigations progressed, questions arose regarding the events that led to the critical fuel shortage over the Atlantic. Doubts emerged about the crew's decision-making, particularly their apparent failure to respond to instrument warnings of rapidly declining fuel levels. In the aftermath, significant changes were made to aviation safety protocols. Airbus introduced a new alert system in their flight management computers to notify pilots of significant fuel loss, an indicator of a potential fuel leak. Additionally, pilot training now places greater emphasis on effectively managing fuel leaks and correctly interpreting non-normal checklists. The final investigative report acknowledged the pilot's failure to detect the fuel leak in time, but praised their exceptional response once the engines failed. The captain was commended for skillfully controlling the aircraft during the engine-out descent and landing under extraordinarily challenging conditions. The first officer was praised for providing valuable support during the glide and landing. The captain and first officer were therefore honored with the Superior Airmanship Award by the Airline Pilots Association. In conclusion, 3 primary factors contributing to the incident can be identified. Firstly, the improper installation of the spare engine was identified as the root cause of the fuel leak. Secondly, the crew's lack of training in handling fuel leak-related imbalances and the absence of such scenarios led them to focus solely on balancing fuel without considering the possibility of a leak. Lastly, cognitive bias played a role as the crew's assumptions hindered their ability to recognize and address the situation effectively. Let's think about what we can learn from this important story. It teaches us how crucial it is to train well. Check equipment carefully and always be ready to deal with unexpected problems. If you enjoyed this video, please consider giving it a thumbs up and subscribing to our channel for more incredible stories. Don't forget to hit the bell icon to get notified about our latest uploads. Thank you for watching.